Hi, and welcome back to Integrated Science. I'm Miss Sparks, and today we are going to start talking about the idea of how the law of conservation of energy can play out with our good old friend thermodynamics. Now, a lot of students get really just confused about the term thermodynamics, or it feels like a big, really fancy word, but all it stands for is heat. And so that's what we're going to be talking about. How is heat transferred to different energy sources? So we've kind of already been talking a little bit about it already, as we talked about how forces can create friction, and friction is just a form of heat that's being moved through a system. So we're going to develop that idea just a little bit more. So far this unit we've talked about work and power, and how work is just the ability for an object to produce energy, either kinetic or potential energy, and we measure those energies in joules. And then we went into the idea that you can always have kinetic and potential energy present in a system due to the law of conservation of energy, which states that energy cannot be created or destroyed. And so we're going to look at that today and kind of think about how we can express that with thermodynamics, or that idea of heat. And so temperature and thermal energy. So do me a favor and please get out a sheet of paper and take some notes today on how we kind of go through and talk about these different types of terms. Maybe. There we go. All right. So first off, once again, thermodynamics, big, fancy word for heat, which is just a form of energy that flows from a warm body to a cooler body. So just think of simple things that maybe it's getting colder outside, it's getting close to winter, so hot chocolate is a great thing to have on a cold day. So you make your hot chocolate, you put it in the mug, and you realize, like, oh my gosh, it is really too hot to drink. So you let it cool off for a little bit. You let that heat expand out into the environment around the cup, which is just a room, and it cools off. And so heat is being transferred. Your body is a great example. You have a temperature. It normally varies somewhere between probably 97 to 98 degrees somewhere. If you were to get a fever, your body is trying to fight off that virus or whatever it may be, so it's going into overdrive. So it's creating more energy to try to fight off whatever bacteria or infection that you might have. So the idea is that it can be transferred all around us. So warm objects lose heat, they become cooler, their temperature lowers. Cooler objects absorb heat and they become warmer, and so things can rise too. So it's this exchange. Heat is not created or destroyed. It's just moving back and forth, back and forth. So we're going to talk about this idea of the kinetic molecular theory, which is just fun to say, molecular, which is just the idea of, we've been talking about things in class with our qualitative and our quantitative data. Is most of the things we've been observing have been really big objects. We've observed the Hot Wheel cars, our marbles. We observed you walking up and down the stairs to find your work and power. So everything's been really big. When we talk about things that are molecular, though, we're looking at a smaller level. And so this is the point in which this class kind of switches just ever so slightly to kind of look at the micro level of objects as opposed to the macro. So macro means big, micro means small. We're going to look at those micro ideas behind it. So sometimes we can't always see this happening as easily as we can see a Hot Wheel car moving down a track. So kinetic molecular theory just states that matter is made up of tiny particles, atoms, when atoms are made of protons, neutrons, and electrons. And we could even go further, but we're not going to. We're just going to stick with our basic protons, neutrons, and electrons. And in a hot body, the particles move fast, and in the cold body, the particles move slow. So it's just meaning that hot body objects have high kinetic energy. They're moving really fast, whereas cold body particles are moving much more sluggish, so they have more of potential energy. And therefore, hot bodies have high kinetic energy, and that's what that's stating right there. So what happens though in the grand scheme of everything in our Earth, our classroom, our solar system, wherever you think, even our universe, if you want to go that far, is that everything is trying to get to an equilibrium. And that just means balance. We've heard this term a few times, and we'll hear it even more as we move through the next couple of units. That equilibrium, that balance of kinetic potential, the balance of force and acceleration, and now we're talking about the balance of heat exchange. So if two objects are brought into physical contact, there is initially a change in the property of both objects, meaning that if I have a cold cup of water and a hot cup of water and I mix them together, there's going to be initially a change in both those properties. Or if I drop an ice cube into boiling water, there's going to be an exchange. They're going to change kind of rapidly. That ice cube is going to be like, melt really, really quickly. But eventually, if I let that water boil forever and ever, that ice cube is going to melt. Or if I take that water outside and it's 32 degrees outside, it's slowly going to stop boiling as well, because that cold air is going to kind of cause it to change. It's going to become what we call thermal or equal. And so what that is saying, and I kind of stopped here, eventually the change in property stops and the objects are said to be thermal or thermodynamic equilibrium, meaning that they're going to become balanced in that the energy has been exchanged from the hot body to the cold and the cold body to the warm, and they've become balanced. And you can kind of see that there's a picture here where I have an object that is really, really warm. Well, here's two that are balanced. The really warm energy is high energy, so it's going to bombard that cold energy very quickly, and the particles are going to say, come, follow me, let's all be high energy. And so they do, and then the cold body finally takes over and says, all right, the energy is being dissipated, normally is a form or a release of heat, and it goes out into, and so then it becomes thermal. I'm going to skip this part here. There we go. So we are going to talk about 3 different laws of thermodynamics. And so they all have to, once again, kind of do with heat and how that energy can be exchanged. The first one's pretty simple. It states that heat cannot be created or destroyed. As simple as that. So all matter has the possibility of transferring heat one way or the next, just depending on what state of matter it is, or if it goes through a physical or a chemical change. But that heat is always there. So I have a picture of your hands, and so when you rub them together, you create friction, which then creates heat on your hand. So like, think of a cold day, you might go outside and be like, oh, I need to get my fingers warm. And so you're just changing that heat. It's not like you're walking around like, man, my hands are hot today. You have to create that, or not create, you have to distribute that energy to kind of incorporate that into your hands to make them feel warmer. So the first law, once again, states that heat cannot be created or destroyed. The second law of thermodynamics is where I want to stay here and talk a little bit about the most, which brings us into a interesting vocabulary word called entropy. And entropy is just the quantifiable measure of how every evenly distributed heat is. That is a mouthful to say, so let me read it again. Entropy is a quantifiable measure of how evenly distributed heat is. It's talking about chaos. And so those of you who have had me before know that I am a big fan of science when it comes to earth science and space. So entropy always reminds me of Jurassic Park, where there is a character, Malcolm, who has the glasses, is talking about the theory of chaos, and that not everything always happens the same way twice, is that it can kind of change. And this is what entropy is kind of talking about just a little bit. We're just going to be measuring the quantifiable distribution or disturbance of an object, aka meaning objects that have high kinetic energy, have high heat, and then have high entropy, because they're particles, their protons, neutrons, electrons, their atoms, their molecules are going to be moving really fast. So objects that have high entropy are normally really hot or very warm bodies, and normally have high kinetic energy. A volcano that is erupting would have high entropy. A boiling pot of water would have high entropy. Trying to think. The sun has high entropy. Energy, totally particles moving really, 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 really fast. Whereas a glacier would have low entropy. The particles are moving really slow. Or even just a tub of ice cream, low entropy. And so entropy is just the idea of system is measured in its degree of disorder. And disorder is we're thinking about the kinetic energy that is moving through a system. So entropy is usable energy decreases in all energy transfers, meaning that not everything stays super hot all the time, that it cools off. A volcano that is erupting at some point is going to lose its heat, whether it's just because it's run out of a magma source or whatever, so it becomes a lower energy. You can even think of your body as a system of entropy. You eat a whole bunch of carbohydrates, you're going to get a whole bunch of energy, and you're going to want to burn that off. You're going to want to run around and do something or whatever it may be. It gives you more energy. So usable energy decreases in all energy transfer, meaning that high energy is going to go to low energy, and low energy always has the possibility to go to high energy. So if entropy increases, less energy is in a usable system, meaning that it's burning some off and it's being released into the atmosphere or its surrounding system. Conduction and radiation may cause energy to be transferred to the surrounding areas. And we haven't talked about these two terms just yet, but we will. Conduction and radiation, which are forms in which energy is transferred. So there's two different types of reactions that I want to talk about, which is exothermic and endothermic. And all that means is exo, exiting, endo, entering or in the system. So all chemical reactions require breaking bonds, which absorb energy, and making bonds, which release energy. These are our chemical reactions. So think about, you've probably talked before in maybe middle school or elementary school about a chemical reaction and a physical reaction. Like a physical reaction is like me taking a sheet of paper and just ripping it in half. I've just physically changed it. If I burn the sheet of paper, I can't get that piece of paper back to its original form. So I've chemically changed it. I've broken the bonds, and that's what this is talking about here. All chemical reactions require breaking bonds, which absorb energy, by making bonds, which release energy. That fire is releasing heat. The overall change in energy results in a reaction that is either exo or endo. So endothermic means that it is coming into a system. Exothermic is that it's leaving a system. So let me show you some examples here. So exothermic, a process that has an overall release of energy. It feels hot because the surrounding heat is heating up. A fire is a great example. The sun is a great example of exothermic. Your body, you are radiating heat out of your body. You are an exothermic body. You are producing heat within, and it's being released without, to the outside. These are some chemical formulas that we're not really going to go into, but you can see that there's a, if we have oxygen and hydrogen, and if we chemically bond them together, that creates H2O. Our water, and then it releases it back, some energy back out into the atmosphere. This is burning sugar, which you can't get that sugar back. Once it's burnt, it's done. And then endothermic is the other process that absorbs. And so we'll talk about this quite a bit when we get to photosynthesis. The sunlight is bringing into the plant, and the plant is creating a chemical reaction. So we're next going to talk about the different ways in which we can have thermal energy transferred. So hopefully this was helpful.